This video was created to show the processes involved in gravitational lensing, time dilation, and the Doppler effect on electromagnetic waves in a gravitational field. The black dot in the center of the image represents a supermassive object. For our purposes, let it represent a supermassive star. The surrounding lightly shaded sphere that fades to black represents its gravitational field. The white lines moving from top to bottom represent light from a distant source that is traveling through the gravitational field. We can imagine it's light from a supernova or maybe a distant galaxy. The letters represent observer positions. Two of these positions have clocks and will represent time dilation. Gravitational lensing is the bending of light as it passes through the gravitational field of a supermassive object. This effect will bend light around a mass, making the source of the light appear as though its position is different than its real location. Looking at the image, notice the electromagnetic waves passing through the gravity well. Notice the shadow that's created when they pass the object. Also notice that the waves bend and begin to fill in the area of the shadow. Observer position D is inside the shadow and will not see the source of the light. But observer position C will see the source because the light has bent around the supermassive object. The bending occurs because of the change in speed of the wave and its angle to the gravity well. The Doppler effect is a change in frequency on a wave as it travels into or out of a gravitational field. When moving into a gravity well, an electromagnetic wave will increase in frequency. This is known as blue shift. When an electromagnetic wave climbs out of a gravity well, its frequency will decrease, and this is known as red shift. Notice the waves begin to slow as they enter the gravity well. The slowing causes the waves to bunch up. This bunching up shortens the wavelength. It happens because the front of the waves begin to slow before the back of the waves. An observer in the gravity well cannot measure any difference in the speed of the waves because time is also slowed identically to that as the waves. This is known as the constant speed of light. For the observer in the gravity well, the waves increase in frequency, resulting in them being blue shifted towards the high end of the electromagnetic spectrum. For waves climbing out of the gravity well, the opposite effect happens. The waves gain speed with altitude, so the wavelength gets longer. The front of the waves begin to speed up before the back of the wave, stretching out the wavelength. The observer in the gravity well will notice a decreased frequency of the waves. They are red shifted towards the low end of the electromagnetic spectrum. Gravitational time dilation is the difference of elapsed time between two positions of unequal gravitational mass. Notice the clock at position A has a different rate as the clock at position B. The clock at position A has a slower rate because of its position in the gravity well. The rate of elapsed time decreases or slows as gravitational mass increases. This is directly proportional to the rate of slowing for electromagnetic waves and is responsible for the constant speed of light. All motion slows in a gravity well. Even electrons in atoms decrease orbital velocity as gravitational mass increases. This is known as gravitational time dilation. In 1964, Erwin Shapiro predicted a time delay for radar beams bounced off Venus. He proposed to measure the round-trip travel time when the Earth, Venus, and the Sun are most favorably aligned. This is known as gravitational time delay. Position C on the left represents the Earth. Position D on the left represents Venus, and the black dot now represents the Sun. In 1966 and 1967, using MIT's Haystack radar antenna, the first successful tests were performed, matching the predicted amount of time delay. The positions C and D on the right represent the round-trip travel time in the absence of a gravitational field. This shows that all motion slows proportionally as gravitational mass increases. Thanks for watching. Hope you enjoyed the video.